Greetings, my wonderful scholars. Still on JAM question 2001, question number 12. Find the frequency of the first three harmonics of a piano string of length 1.5 meters if the velocity of the waves on the string is 120 meters per second. In this question, the exam body targets to know your understanding of harmonics. Harmonics in a layman's word is vibration, repeated vibration. You can see the question is making reference on piano string. A piano string makes series of harmonics, vibrations. The natural vibration of a piano string, even when a piano string is not being disturbed, is vibrating. Is vibrating, and that vibration is called its natural vibration or natural frequency. It's natural frequency, or in other words, first harmonics. The first harmonics is the natural vibration of a body. Then the second harmonics is twice its natural frequency. That's the second harmonics, also called the first overtone. Okay, the first harmonics is also called tone. Then the second harmonics is called the first overtone. And the third harmonics is 3 times the natural frequency, and it continues that way. That's why it's called harmonics, repetition of vibration. And the first harmonics is the tone, is the natural frequency of that body. Example, string, piano string. Then second harmonics or first overtone is 2 times its natural frequency. Third harmonics is 3 times its natural frequency. Fourth harmonics, 4 times its natural frequency. So to give you a clear example, let's take human voices as a point of emphasis. Bars can be considered the first harmonics. Alto, tenor, soprano, second, third, and fourth harmonics. Because you make the highest vibration in soprano and the least in bars. So the bars can be considered our first harmonics. Okay, going back to the question. The question is demanding for the first 3 harmonics, first, second, and third. The best way is to bring out your parameters. Let's see our parameters from the equation. Solution. Okay. We're given length 1.5 meters. We're given velocity 120 meters per second. We're looking for harmonics. Recall, harmonics deals with frequency, vibration, first, second, and third. So first frequency, unknown. Second, unknown. Third, unknown. Okay, see how we solve it. Let me use a diagram to make it simple. Draw the piano string. Let this be our piano string. Recall, this is first harmonics. First harmonics. In every piano string, the string must be fixed to 2 ends, 2 extreme ends. That's what I've done here. In waves of vibration, anywhere there is a fixed point, anywhere there is 0 vibration or no vibration, we'll call it node. Node is a point in a medium where there is no vibration in that medium. Therefore, these are nodes. Node 1, node 2. A piano string will have 2 notes at its ends, because at those ends there is 0 vibration or no vibration. Then another point in a medium where there is maximum or highest vibration, we call it antinode. Therefore, in the first harmonics, please pay keen attention to node and antinode arrangements. In the first harmonics, we have 2 notes for a piano string and 1 antinode for a piano string. I'll keep the antinode here. Then let me now draw my wave. Okay, notice. In the wave diagram there, we were able to get just a kind of half a circle or angle on a straight line. That's what happens with having 2 notes at the extreme ends. The gap from one node to another node is half wavelength. Recall, wavelength is the horizontal distance in a wave that marks angle 360 degrees. Pay attention. Wavelength is the horizontal distance in wave that must mark angle 360 degrees. Observe, from node to node, we're having 180 degrees. From node to antinode, we always give you 90 degrees. 90. Antinode to node again, 90. 90 plus 90, 180. So the interval between two nodes is 180 degrees. Therefore, considering the length I was given from my parameter, the length of the piano string is 1.5 meters. L is equal to 1.5 meters. Then in solving harmonics, we'll make comparison between the length of the medium or the music instrument and the wavelengths. Then let's do the comparison. Then the length here is 1.5. You can see that 1.5 meters. Then its equivalent to wavelength becomes, recall, this is angle 90, total angle 180 degrees. Therefore, 180 is not a complete wavelength. A complete wavelength is 360 degrees. Therefore, 180 is half wavelength. In the first harmonics, a piano string will give us half wavelength. The length is half wavelength. So let's go on. Recall, harmonics is frequency. But let's go on with the wavelengths. Okay, to get wavelength from what we have there, from the length given, we'll be having 1.5 is equal to 1 times wavelength is wavelength, all over 2. Okay, let's get our wavelengths. Make it the subject. This over 1, cross and multiply. Our wavelength times 1 is wavelength. 2 times 1.5 will be giving me 3. Recall, wavelength is distance, horizontal distance. To take the unit meter, we've gotten our wavelength. But recall, we are actually looking for frequency. Harmonics is vibration. So to get our frequency, frequency is equal to V over wavelength. This is how we're finding frequency in wave. Okay, then let's solve. Recall, we're giving speed earlier, 120 meters per second. Okay, then to get the first harmonics, that's the frequency now. Fundamental frequency, first harmonics. Our V is 120 meters per second. Our wavelength is 3, from what we solved, 3. Then 12 divided by 3 will be giving me 4. Drop down your 0, 40 Hz. We've gotten the frequency demanded. The first harmonics or the fundamental frequency, which is what? 40 Hz. Then recall, this is the fundamental frequency. In other words, the first harmonics. And recall what I said. I said earlier that once you get the natural frequency, the second harmonics is 2 times the natural frequency, and the third harmonics is 3 times the natural frequency. Therefore, the first harmonics is 40 Hz, second harmonics will be 40 times 2, 80 Hz, third harmonics will be 40 times 3, 120 Hz. From our option, the correct option there you can see yourself. Option A. Thank you. Stay tuned as we push ahead.